All right. Let's get started. So today, let me fix this. Today is day 4, AASL 2. This helps me remember where we're at. We're going to be going over IB 5.3, which is basically derivatives. Have we ever heard of derivatives before? Have we done simple basic derivatives, or is this just our very first time hearing the word derivatives?
I've never heard before.
Cool. This is one of those things that is like a lot of teachers would think about, like calculus day 1, or when you have a student who says like, I'm so scared of calculus, a teacher could be like, I'll teach you calculus in 5 minutes, and they'll teach you derivatives, because it's just basically the essence of calculus. Now, the good news is that derivatives are relatively simple when you start, and what we're going to be doing for 2 weeks, 3 weeks is just harder derivatives and harder derivatives and harder derivatives. You almost want to think about derivatives like a brand new algebra that you're doing, even though they're not really algebra, they're kind of like calculus. So this is going to be very heavy on functions and polynomials, a lot of f of x equals x squared plus 3x, a lot of that kind of stuff. If you're pretty good at algebra, then typically this stuff is just another step. I wouldn't think of this like some mega way harder step. It's just one more step past foiling and factoring and all that kind of stuff. So let's talk about derivatives and what that is, or what that even is. I'm going to start by drawing a nice graph here. I would recommend you kind of sketch it out. It doesn't have to be perfect, just getting some kind of graph on here. And this is a nice linear function. It's a line, it's a straight line. And so we could ask ourselves here, put a 2 there, what is the gradient at x equals 2? God, this pen is so whiny lately. What is the gradient at x equals 2? As it stands now, I just kind of drew a random picture up here and we don't have enough information. So if we, let's just say, add something else to it, let's add the function here. Let's say this is y equals 1/3 x plus 1. Just kind of making something up, whatever it is. What is the gradient at x equals 2? What do you guys think? The gradient is the slope, of course. We definitely should be able to do this fast. What we got? We got an answer? Definitely don't need a calculator. We just are looking for the gradient, which is the slope. Here's our equation. 1/3, right? Because our slope comes from in front of the x. And so at x equals 2, the m equals 1/3. And if I ask you another question, what is the gradient at x equals 100, what would the answer be there? 1/3. Nice. That's what we like about a nice linear graph, is that it's really boring, right? There's really not all that much interesting to it. There's, 1 at y-intercept, 1 x-intercept sometimes, and yeah, it's the same, pretty much it's just gonna go on and on and on. The gradient is nice and boring. We are gonna wanna make sure that we know the gradient formula, which again, I'm still getting used to calling it the gradient formula. It seems like they're very serious about that, which is m equals fraction y minus y over x minus x. It's rise over run. Make sure, you'll see sometimes a bunch of 1s and 2s on this formula. You need to make sure that they're kind of stacked up vertically, the coordinates. So if you have a coordinate right here, that is 2, that's gonna be 2 and on, but let's say you have some thing here, I'll just make it up and get rid of our function here. 2, 2, let's make it 2 and 3, so they're different numbers. Well, the y value 3, you cannot put the 2 in this position. That would be a mistake. You have to go underneath. And so that's why sometimes you see like y1 or y2, that doesn't really matter. Just make sure they're stacked on top of each other. We'll go to the gradient formula. Now, this linear graph is just a nice constant gradient, but we start to get some issues very quickly when we look at basically any other type of graph, any other type of function. In particular, everybody likes to start with a quadratic. We take our x and we bump it up to an x squared. So now we're dealing with this thing, it's quadratic. And now we have more of an issue. Now we say, what is the gradient at x equals 2? And now we're a little nervous because the slope or the gradient at x equals 2, our curve is not just a straight line. We can think about algebra 1. We can say, well, over here, this is a positive gradient because we're going up, and we can look at over here, this is a negative gradient because we're going down. It's the intervals of decreasing, the intervals of increasing. And we can tell right away if for this portion of the graph, your slope is bigger than 0, and for this portion, your slope is smaller than 0, your slope changes. Somehow it has to get from less than 0 to bigger than 0. So it is changing over time. So that's kind of messing up our whole nice constant slope, our nice just grab the m from the formula. We need some other way to do it. Now, that's going to introduce, I wonder if I can undo all this, perfect. If you still have it on, that's fine. That's going to introduce a couple different types of gradients. So one of them, let's say that right here is 4, and let's give this the point 4, 2, and let's give ourselves another point. Let's go right here. This can be negative 1, negative 1. Over 4, up 2, left 1, down 1. And so we could find the average rate of change. So this is one of those things where we kind of want to lock into some vocab for a second. Average rate of change. It's a little vocab moment. Vocab. The average rate of change is like the average gradient or the average slope, and the average rate of change is just the slope formula. M equals fraction, y minus y over x minus x. Again, if you want to put the little 2's and 1's, you know, go crazy. And so we could find the average rate of change over these two, over this region, which would look something like that, by just calculating it using the slope formula. This is one of those things that a lot of times we do on the very first day, right now, when we're going through the notes, and then maybe we do a little bit of homework, and then we come back, and 3 days from now, I say, what's the average rate of change? And everybody looks at me like I'm crazy, almost because it's too easy. The average rate of change is just the slope. So we could do that for this question really quick. The m would be equal to, let's call this one 0.2 and this one 0.1. So we'll use this one first. The y is on top and the x is on bottom. The formula has subtractions, and then we'll call this 0.1, and it's negative 1, negative 1. So that's pretty easy. Negative 1, negative 1. That's going to be 2 plus 1, which is 3, and 4 plus 1, which is 5. So our average rate of change is 3 over 5. Now that average rate of change is not the exact rate of change at any one place. That is just the average rate of change from there. So if we're looking to find the gradient at x equals 2, it has not worked yet. We have not found that exact instantaneous rate of change. So now we're gonna introduce our second vocab term. And this one sounds a little bit more crazy, but it's, again, not all that crazy. The instantaneous rate of change. So the instantaneous rate of change is that rate of change exactly at the exact same point. So that means that if we're looking for the gradient at x equals 2, that's it. We're not going to be considering any other coordinates. We're not going to be doing average rate of change. We want to know exactly this. What is the slope at that point? Now next, again, this is another little vocab word, instantaneous rate of change. And lastly, we're going to introduce one more vocab word, and that vocab word is tangent line. So a tangent line is a line that touches our graph here, but it touches it at only one point, and it doesn't cross through our graph. So it's going to do a nice kind of grazing of our graph. It's going to just like shave it off. So what this tangent line is it is a way to visualize the slope at this exact point, this instantaneous rate of change. So, everywhere we could look for a tangent line. We could look, if we wanted to, find the instantaneous rate of change over here at -6, and we could visualize that with a tangent line. A nice little slice of our graph. Or we could even look down here at the bottom, a nice, just barely kind of touch. It's almost like you're balancing a plank on your knee or something. I don't know. That's not the best analogy anybody's ever made, but you can see how now that we visualize those tangent lines, you can see our slope changing throughout our curve. It starts off negative, very steep, it is starting to balance out, and then it starts to go back up. If you make a whole bunch of these tangent lines, you can really see how it shifts over time. None of those tangent lines cross onto this side of the graph. Just beautiful. So our tangent line is a way for us to relate those very easy linear graphs where the slope was super easy to find to this more difficult changing. Our tangent line is a line. And so a lot of times we'll be talking about the slope of the tangent line. Handwriting is just awful today, but we'll get over it. We'll talk about the slope of the tangent line, and that's another thing where, next time I see you will be Friday, and then I'll see you on Tuesday, and like when I see you on Tuesday, I'll say something like the slope of the tangent line, and one of us might just be like, whoa, slope of the tangent line, that sounds crazy. The slope of the tangent line is the exact same thing as the instantaneous rate of change. Because if I want to know exactly what my instantaneous slope is, well then I could just say it's the same as the slope of the tangent line. So a lot of these things sound very similar. We're about to move on, but let's just kind of look at the vocab that we've got so far. We've got the average rate of change. That's when you're looking over a region. And that's a very easy thing to do, just do your slope formula. Then we have our instantaneous rate of change, which is that slope at an exact point, and we can visualize that with a tangent line, or the slope of the tangent line, which is the same thing as the instantaneous rate of change. So we've gone through 3 here. Average rate of change is kind of old school and easy. Instantaneous rate of change, tangent line, these are basically the same thing, and that's the new stuff. That's kind of the new school stuff. Okay, how do we feel about that? Again, most of this is kind of like okay, but what does a problem look like? Okay. If we have the function f of x equals x squared, that is a quadratic graph. If I was going to sketch that real quick, I'm drawing a nice U-shaped graph. It's going through the origin. It's an upwards facing even graph. All things we can bring back from math analysis, we can bring back from the first year of IB. And okay, if I want to find the instantaneous rate of change, that's when I'm going to bring in the derivative. Okay, so we're going to say take the derivative. So you might see a question that says take the derivative, or you might hear me say take the derivative, or of course people could say like, what is the derivative? The derivative of this question is written like this. And so the derivative is dealing with this little hash mark, this little apostrophe. It's very importantly after the F, but before the parentheses. If you put it anywhere else, it's just silly. It has to go in that position. And that just denotes that we've gone to the derivative of the function. Okay? This is our derivative, and we'll talk about where that came from in just a second. What the derivative does is the derivative is the slope finder. The derivative will say, give me any value, so input x's, input x, output n. Give me any x you want, and I'll tell you the slope. For this question, it's very easy. If I wanted to know, for my graph over here, what is the slope at x equals 3? What is it? 6. And how did you get 6 so fast? You input the x, and what's 2 times 3? 6, so you output the slope. Now let's look at our graph up here. The slope at x equals 3, okay, that's over here somewhere. And the slope, the instantaneous rate of change, the slope of the tangent line, is looking something like that. Now for our graph, if we put in a negative number, we should be getting a negative. So let's try it real quick. What is the m at x equals -5? What do you think it is? -10, that's very easy. Here's our slope of the tangent line. Boom. Okay, great. Now, these questions are too easy. It's a waste of time. I'm not just gonna give you the derivative and ask you to use it. It's gonna be your job to take the derivative. So, what we wanna do is learn how are we getting from the original function here, x squared, down into f prime of x equals 2x. So, Ian, you said you'd kind of seen this before, learned this before. Do you know how to go from the function to the derivative? So if we just had to guess, look what we got, x squared, and look what we ended up with, 2x. How do you think derivatives work? How do you think you go from one to the other? All right, so Colin just showed up this morning. He said, listen, it looks like you move the exponent in front of the x. I don't know. And he's right. That's what you do. Okay, so derivatives, again, people are like, oh my God, calculus is so scary. What we're going to learn today is derivatives. And yeah, not only did I not even teach you it, Colin basically came up with it on his own, and he was right. So let's look at more examples and kind of how does this actually work. So this is going to be called the power rule. Everything we've done so far is the foundation and like the theory of calculus. Why are we doing this? How does this work? What we're about to learn is actually what your homework's about, the power rule. So if you want to like, this is the most important thing you're gonna have on the whole piece of paper, right? This is the meat and the bones of what we're learning today. The power rule is how you take a function and you find its derivative when it's nice and easy. So we're gonna say if f of x is equal to ax with an exponent of n. Now that's 3 letters, but we'll talk about it in just a second. Then f prime of x is equal to nax n minus 1. Maybe thinking for a second, whoa, I thought this was just move the 2 out front, like Colin said, what the heck's going on? It's still the same thing, we just need to kind of be mathy about it and show everything. So first of all, this a is just a constant. That would be like 2x squared or 4x squared. When you have a polynomial, a lot of times it looks like, 6x power 5. So this 6 is just the a. And when we take the derivative, that a is not going anywhere. That a is just a normal old a. So when we take this derivative and when we put this 5 in front here, and it's going to hang out with the 6, that's why our n has moved out front here and it has become an n in the front hanging out with the a. So the constant, the coefficient that was already there is not going to move. When this 5 comes out front, it's going to join up there. These are right next to each other, so are we adding, multiplying, or what? Multiplying. So we're going to be multiplying those numbers together. That's not too bad. You also can think of, for the last question, if it was x squared, it's kind of like a 1x squared, right? And we have an invisible 1 in front of all of our polynomial terms, whatever. It's the same thing. The 2 comes in front, and it's 2 times 1, and who cares? It's going to be 2. Now, this is the part we haven't talked about. You can't just be moving stuff around. And so for the last question, when we moved this 2 in front, okay, nice, that wasn't too bad. But what did it leave behind here? It actually left behind a 2 minus 1. 2 minus 1 is a 1, and so it's just a 1 up there. So when we see 2x as our answer for that question, it actually is a 2x with a little 1 power, which again is one of those things we don't really care, right? It's an exponent of 1, doesn't really matter all that much. Now, let's kind of finish with this thing up here because I scratched it up here. We've got that 5, which is going to come in front and multiply with the 6, but what is going to remain as the new exponent? A 4. And before we look at some questions here, this ain't that hard. You move the number out front, you do some multiplying, okay, sure, and you gotta subtract 1. That's not that hard, okay? Sure, we can handle that. Okay, now, let's speed it up, because like I was saying, that is not really meant to be very hard. We're gonna go through some questions really quick here. We're gonna do all 3 of these. F of x equals x power 8. What is f prime of x gonna be? Shout it out if you got it. 8x, and then take away 1 from that 8. 8x to the 7th power. We can do it basically in our head. We can do it 5 seconds. Nice, that's where we want to be. G of x. G of x can be 5x cubed. Shout it out if you can get G prime.
10x squared.
No.
13x squared.
Right, so we still need that 3. We can't drop it to a 2 right away. The 3 comes out front and makes a 15. And then the x cubed drops down to an x squared. I kind of think about it like our equation is kind of degrading a little bit. We start with cubes and then it kind of degrades into a square. Or we start with squares and it kind of degrades into just a normal x1. We get it. wasting my time. Let's keep going. Now, what if we have polynomials? Because again, we can't just do these questions where it says 5x squared and we can do them in 3 seconds, right? We surely have to get more complicated than that. So a polynomial is basically going to be one of those things that's like a string of math, right? If you're nervous about what a polynomial means, it's just a bunch of things in a row. Poly meaning many. So I'll write that like g of x plus h of x plus k of x, right? It's just like thing plus thing plus thing. So what do you do if you have this string and they're all added up together? The good news is polynomials, easy. You just take the derivative of each of them, totally separate from each other. So we can think about it one at a time, and f prime of x is going to be g prime. Just take the derivative of g. You don't even have to worry about h. You don't have to worry about k. Just one at a time. Up next, h. Just figure out the derivative of h. You don't have to worry about the g. You don't have to worry about the k. And lastly, go ahead and get the k. Basically what this means is when you build a long polynomial, it doesn't change the rules. You just take them one at a time.
Good morning, teachers and staff. Pardon the interruption. At this time, we are going to have a junior assembly for all of our 11th
That's not us,
graders.
right? Good.
If you
All right, we're going.
have-
Let's see. Write this down quick. We're moving on. 5x cubed plus 3x squared plus 10x minus 1.
We're going to ask you to sit with them. And again, this is 11th grade students. But if you have a class that's a majority of juniors, and you have
We're gonna work on
please feel free to take them
the
with
derivative here.
Thank you.
We're going to work on finding f prime, which is a sneaky vocab thing that I've snuck in there that we say prime when we're talking about these little hash marks. I'll give you another 5-6 seconds to work on this, but this honestly should be something we can basically do in our head. There's 4 terms here. We've got term A, term B, term C, and term D, and there's 4 of us in class. So everybody's responsible for one of them. If there's an easy one, go first. Does anybody know what term A, what do you got?
15x squared.
Nice. I'm pretty sure we literally just did that one. So, nice. Bonus. Okay? Excellent. Now, you didn't have to worry about B, C, or D. Just do them one at a time. Up next, B. Who's got that? What do you got, Colin?
I have 6x.
Plus 6x. Again, I think of it like we're degrading. We started off with a cube, then went down to a square. We started with a square, then we went down to an x. We got C and D. What do you got, Lee?
10.
Just a 10. Excellent. We talked about how everything's kind of coming down 1. A little bit funky here. This is like an x power 1. We bring the 1 out front. 10 times 1 is 10. And then we end up with subtracting 1 away from that. 1 minus 1 is 0. It's dead. So we have just a 10. Very good. And lastly, Sailor, you feel confident about D? So it's all degrading by 1 power. We have 3 and it goes to 2, 2 and it goes to 1, 1 and it goes to 0. And if it's all degrading down, and this 10x, which used to not combine with this negative 1, if we bring down this negative 1, now these two things are going to combine. And really, they're not supposed to be on the same level. Everyone, it's like a staircase. Everybody gets stepped down, and they still shouldn't match. These two things didn't work together after the derivative. They still don't work together. These two things don't work, they still don't work. So what can we do with this 1 to bring it down, but it's not really allowed to combine with that 10? Think about it like this. What if it was x0? That's kind of like what's going on there. 3 x's, 2 x's, 1 x's, 0 x's. And we're going to need to bring the 0 out front what happens with constants is that they're just zero. The derivative of any constant is just zero. So this right here, zero. So we don't need to write it. We don't need to put plus zero, of course. And let's think about that for just a second. Please, there you go. Constants. If we think about from the last function, let's just say k of x was equal to -1, okay? That was because I was thinking about chopping up that polynomial. We can do them one at a time. So we're allowed to think about just this function. If -1 is its own function, how does this graph look? It's a line. And what type of line? Horizontal. It's a nice horizontal line. So that's how our graph looks. And the derivative calculates what? The slope. And what is the slope of this?
0.
0. So it makes sense, right? It's not just like a funky trick. It actually makes sense why constants are 0. So if you see, you'll see a lot of times a question like this. Y equals pi. Right? And they'll try to give you pi. And they'll look for an amateur calculus mathematician to say, ooh, pi is super fancy. The reality is pi is just a number. It's a strange one, it's an irrational one, it's a useful one, but it's just a number. It's no different than -1. And so what would y prime, another sneaky introduction of new terminology, but what would y prime be?
0.
Just 0. The derivative of any constant is equal to 0. If you need to write that down, derivative of any constant equals 0. Oh no, can't have the lights on. Cave people. Yeah. At least I'm a cave person. I won't speak for you guys. Okay. Now, at this point, let's just do a little bit of a check. That is not how you spell check. Let's do a little bit of a check and see if you can, kind of know what's going on. G of x is equal to 6x power 7 plus 3x squared minus 5x plus 111,110. Can you find g prime? Can you take the derivative? Taking the derivative, power rule, polynomial. All right, did we get 42x power 6?
Yep.
Nice, put the 7 with the 6, easy, move it down, minus 1, cool. Did we get 6x minus 5? And what about this nightmare number?
Any constants.
Who cares? And because think about it like this number, all it does is move the entire shape up or down. So if this is the shape and it's moving up or down, crazy math teacher moment, it's not changing the slope of the graph at all, right? If the slope is still 5, the slope is still 5, who cares? So that's why we don't really care about that. Now, what does this do? Why find g prime? What can we do with g prime? It's already in the notes, we already talked about it, more review. We can find the slope. Remember, this g prime is the gradient. Maybe we'll, this is the gradient finder. This right here is the most insane function I've seen in a week. I don't have any idea how it looks, but I can tell you exactly the slope at any point you want. Now, those numbers are gonna be very big because we got an x power 6, but let's just say I want, find the gradient at x equals 1. That should be relatively easy to find. We might be able to do that one in our head.
42 to the 6th power.
No, because you plug in the 1, and it's 1 to the 6th power.
And then times 42.
And then times 42. So I wouldn't make you do 42 to the 6th power. I think your calculator might struggle to do that. So that's going to be 42 plus 6 is 48, minus 5 is 43. So you can find the exact slope whenever you want. So don't lose track of why do a derivative. It helps you find that slope. We could also call this the instantaneous rate of change. We could also call this the slope of the tangent line. All of those things are the same. It is not the same as the average rate of change, which is just the boring slope formula. Okay, now, even this, very, very easy. We have done a lot of work to teach you all the ins and outs and why this and that. But if it was my job to teach you 7 times 6 is 42 and then subtract 1 from, like, you could have learned this in 7th grade, right? You take that number, move it here, you subtract 1. That's all very easy. Of course, there's going to be questions where it ramps up a little bit. So, we are going to, I'm not going to say the last thing today, but very near to the last thing today. We are going to be talking about this is still, again, going to be a lot of review. We're going to be talking about rational exponents. And sometimes you'll see it like this. It's like a Q with like line. You guys know this? You guys know this thing? It's like an R with an extra line, and it means real. It's the same thing here with the Q, right? It's like a Q, but it's got those extra lines on it. It's like a mathy, fancy Q. Rational exponents. We talk about real, which just means anything that's not imaginary. What does rational mean? Do you know that? I was terrible about these when I was a kid, so I get it. Do you guys know what rational means? Rational means fraction. It's easy for me when I think, okay, I don't really know what rational means, but what does irrational mean? Irrational is like pi, which specifically is a decimal that cannot be a fraction. So then I go, okay, well, if irrational can't be a fraction, then rational must be a fraction. So that's how I do it in my head. Fraction. So what we're trying to do is fancy Q exponents, aka rational exponents, aka fraction exponents. Do we know about fraction exponents? X to the 1/2 power. What the heck is that?
To the square root of x.
Yes, nice job. This bottom number here, let me zoom in a bit. This bottom number here is the root. And the top number here is the x inside the root. So what we have here is 1x on the inside of a square root. And so this looks like square root x. And you're going to need to know how to do this. You're going to need to know how to convert those. Again, ideally you've learned this before. We could see something like x to the 3/5 power And we're just right now working on rewriting that. How do you rewrite x to the 3/5 power? It's a fraction exponent, so it's got something to do with roots.
The square root of 5, or the fifth root of x to the 3rd.
Very good, very good, very good. The 5th root of x to the 3rd, that was a certified first period moment. No stress at all. Yes, the 5th root of x cubed. You have to be able to switch back and forth between those things. And again, that is not difficult. That is a small little memory thing. There's no difficulty baked into that. It's just a reorganizing of things. And the last thing within this rational is that also includes the easier numbers, right? You guys, and don't draw this. You guys know how this kind of works, where here's the natural numbers, and here's the whole numbers, and here's the integers, and here, you guys know, they build up on each other. So when we say we're working with rational exponents, that means we're working with all different kinds of stuff. Natural exponents would be very easy. Whole exponents, the whole numbers includes the number that looks like a whole, which is 0. Do we know what x power 0 is? Do you know what that is?
1.
Yes, anything power 0 is 1. I don't care if it's 30 power 0, it's 1. So we gotta know that. Let's keep it going. After whole numbers, that's 0, 1, 2, 3, 4, 5, 6, 7, 8. We need to introduce the negative numbers. That's called integers. So what about integer exponents? What about x power -2? This is gonna be something we're gonna use an insane amount of times. This is like, we're using this all the time. What does a negative exponent mean? Okay, so a negative exponent is a thing. It could be a negative exponent on top of a number, but most of the time it's gonna be on a variable. A negative exponent is a thing that is on the wrong side of a fraction. That's the easiest way for me to think about it. So if I see something like this, a -2, b -3, do not clear, please. C 5 and D -2. All of these things that have negatives are basically sad that they're on the wrong side of the fraction bar. So, for example, up top, this a, which is an a squared, it's just an unhappy a squared because it's up there in the numerator. It wants to be downstairs. When I used to teach Algebra 1, it would be like, okay, there's a party, and upstairs it's a dance party, and downstairs it's a nice chill hangout, right? And this a to the -2, they're not a mean person, they just don't want to be dancing, they want to be chill. So you just move them down here. Now, once they get down here, they shouldn't be sad anymore. This is where they want to be. So they're just a plain old a squared, because now they're happy. What about this d -2, right? This person's a rager, they just want to dance, man. So put them on top. And now, please. Now it's just a normal little d squared. And then of course, at this point I'm going too far, but we need to finish the question. Cool. So you're gonna have to know how to move a negative exponent means do this. A lot of times you're gonna see something with a negative exponent or maybe a fraction, and you're gonna have to handle it by bringing in those negative exponents. So how could you rewrite x to the power of -2?
1 over x squared.
Nice job. 1 over x squared. Okay. We're gonna put all this together. We're gonna do 2 quick examples. Then we're gonna wrap up. Example. Let's go for L of x this time. L of x is equal to Let's do this question. Now, L of x, we know how to do polynomials. We really like it when it looks like 5x squared, 6x cubed. This looks a lot more complicated. We got fractions, we got variables in the denominator. Variables in the denominator are always a problem. So, this is not going to be as simple as just take that exponent and move it down. Unless we can rewrite L of x. It is still L of x. We have not done the derivative yet. We have not taken the derivative yet. But if we rewrite this, we can think about this as 1/3 x to the negative third power. And I know we just were trying to deal with negative exponents and make them happy by moving them down. But actually, if we make this x cubed unhappy, this reminds us of the stuff that we were just doing. This, we could apply the power rule and it wouldn't be that bad. So same thing here. That's going to be x to the negative 2. This one, when we move this x to the numerator, it's going to be x to the negative 1. And when we're dealing with that, that's a 1/2. What's going to happen when we take the derivative of that? It's going to be 0. So you know what? I'm not going to worry about this at all. Alright, I'm just going to let that exist for the next 3 seconds because it's about to be obliterated. Okay, now let's do it. Let's take the derivative of L of x, L prime of x, and that means we need to do the power rule. Take the exponent, put it out front as a coefficient with the old coefficient. So when we do that, and we move this negative 3 in front, it's going to be joining a 1/3. And what is negative 3 times 1/3? It's just negative 1. Now, if we had another 5 hours, I could sit here and write negative 3 parentheses 1/3 parentheses. Right, we could do all that, but at the same time, we don't have forever. So I'm just kind of trusting that you guys are following. The negative 3 comes up front, it multiplies with the 1/3, and it makes negative 1. Now, what about the x?
-4.
Right. A very common, I did this homework on the bus, or a very common, I did this homework while I was playing Fortnite the night before, is that people will say negative 2. Because it's like, oh, 3 goes down to 2, but we're in the negative. So of course, if you subtract 1 from negative 3, you're going to negative 4. Nice catch, just something to be careful of. What about the next term?
-1x to -3 x cubed.
So we got some parts right, but not the whole. It's definitely going to be x negative 3 power. But when this negative 2 comes in front with a negative 1/2, I know we're going to have negative negative, so I know we're going to have positive. And then 2 times a half is just a 1. So we can put a 1 if we want. I guess we did it on the last one. Over here, what is this term going to be? Negative x to the power of negative 2. Again, our equation is kind of degrading, right? It goes from negative 3 down to negative 4. It goes from negative 2 down to negative 3. And you can hopefully see that it's all stepping down at the same kind of rate. And then what happens to our 1/2? Dead. Okay, importantly, in any math class, we can never end with an ugly exponent. And so these are correct, but these are ugly exponents. So what we want to do is rewrite one last time. We still need this little prime slash here. This first term, if we rewrite it and we make it beautiful, is gonna be negative 1 over x power 4. And the next term, if we rewrite it and we make it beautiful, is gonna be 1 over x cubed. The next term is gonna be negative 1 over x squared. A nice little pattern there. Chef's kiss. And that 1/2, then convert. Okay, we will pick up the radical stuff. The very last thing that we're gonna do today is if you checked out the Canvas, or if you, oh nice, I still have a lot of room left, perfect. Not a lot of room left, we'll see, all right, big online. If you checked out the Canvas, or if you have that unit that I gave you, next time I see you, we will be having a quiz. Now, what is that quiz gonna be on? That quiz is gonna be on memorizing. Your job is going to be to memorize 14 derivatives. Most of these, half of these are incredibly easy. The other half are just, you have to memorize them, okay? The thing about the power rule is that the power rule is great, but it doesn't really work on sine, right? You can't really take the derivative of sine. So some of those things we just have to memorize. So we're gonna make a list here, and when you show up on Friday, I'm gonna give you a quiz that is 14 questions, and you got 7 minutes to do it, and it's no pencil. All you gotta do, oh, there's a pencil, but you just gotta write the answer. Derivative of this is that, derivative of this is that, derivative of this is that. So, let's talk about memorize the power rule. There are 4 derivatives here that you have to memorize. And again, we just learned the power rule, so a lot of these are gonna be pretty easy. What is the derivative of pi? 0. There you go. You got one answer right on the quiz, and we haven't even written these down yet. Awesome. What is the derivative of x? Just 1. Because this is like x power 1, and you move the 1 out front, and then that 1 becomes a 0. Right. Everything degrades down. Nice. Okay. Now these two we just worked with. 1 over x. Now we could figure this out, but every time we come across this, we don't want to have to figure this out every single time. 1 over x is the same as x to the negative 1 power. Then you can put that negative 1 out front, and then you can subtract 1, making it negative 2. And so the derivative is negative 1 over x squared. We just did that. But hopefully we want to get to the point where we can memorize that, because that is a little bit annoying to do. And the next one is the square root x. This is the last one for the power rule. The square root x, okay, we talked about how that works with exponents, but we never actually did the derivative of that. So let's see how that looks. The square root x, how do we rewrite that?
X.
Right? X to the 1/2 power. And then now we can use the power rule. That 1/2 goes in front. So we're gonna have 1/2. Then we subtract 1 from that exponent. And so what is 1/2 minus 1? Negative 1/2. And if we're gonna write this properly, what happens to that negative 1/2? We slide it down to the bottom. So we have 1 over 2 square root x. Again, that is doable, but we don't want to have to take that 30 seconds every time to. We want to memorize these. Okay, if you get to the quiz on Friday and you forgot what these were, well, okay, maybe you have 30 seconds to spare. You can just do the power rule and you can remember, figure it out. All right. Up next, we are going to learn trig. When it comes to trig, how many trig functions are there? 3. Have you? Are there only 3? Have we ever heard of all 6?
Yeah.
There's,
There are 6. We're gonna learn.
yeah.
There is, of course, SOHCAHTOA, sine, cosine, tangent. Sine x, and cosine x, tangent x. And then, in addition to these, there are some other ones. There are cosecant x, secant x, and cotangent x. It's kind of like there's 3. Sine, secant, tangent, and then there's the cosine, the cosecant, and the cotangent. Now, what are the derivatives of these? Well, we're going to start off, and it's going to seem like it's going to be the easiest thing ever. The derivative of sine is cosine. Beautiful. What do you think the derivative of cosine is? Sine. Except for every trig that is a co-something, the derivative becomes negative. So that we can go ahead here. The cosecant is going to have a negative and the cotangent is going to have a negative. Now, these 4 are not quite as easy as those 2 where they trade back and forth. They do have to do with each other, but it's not just a 1-for-1 trade. So, tangent is going to be secant squared x. Now, before we guess, which one should we guess next? There's kind of 2 ways to think about it. Do you think we should go to try to figure out secant next, or do you think we should go to try to figure out cotangent next? Okay. This is where we kind of get into an issue because it's not tangent squared, which would be beautiful, but it's not. The derivative of secant is secant x tangent x. At this point, we should be able to fill out the rest of them. So if regular tangent made secant squared, what do you think cotangent is going to make? Cosecant squared. And if regular secant made regular secant, regular tangent, cosecant is going to make
Cosecant, cotangent.
nice. All right. All of a sudden, that's a little crazy looking. Okay. We'll talk once we get these last 4 down about an easy way to memorize those. The last 4 that we want to memorize are the log. There's 4 of these. Okay. To be 100% honest with you, these log 4 are the difference between the A students and the non-A students. Okay? It's always these log students where there is only a third of the class that memorizes these. nobody likes logs. It's the reality. Nobody likes logs. But here we go. The good news is some of these are actually very easy. A to the x power, which would just be like 2 to the power of x, 3 to the power of x, becomes a to the power of x, which is very nice. And then we have to throw on there also a natural log of a. And it's like, wait a second, that started off nice, but now it's kind of hideous. Okay, this isn't that popular, I'll be honest. By the time Christmas comes around, we might all do 2 of these problems. E to the x, which is basically the same thing, except for E is a very specific number. E is a number we typically use for exponents. It's a number used for insurance a lot of times. It's compounding rates. If we follow the same pattern over here, a to the x was a to the x, so this should be e to the x. And then that one was ln a, so what should this one be?
LNE.
And what is ln e?
Natural. Well, I can also.
Nice, because ln e is just 1. And so that's it. E to the x is e to the x. When we're doing problems, e to the x is a dream. Because you literally don't have to do anything. Take the derivative, cool. I can take the derivative 500 times in a row for you if you want it. Okay? The log base a of x, kind of ugly, 1 over x ln a the ln of x, which is the log base e, should be 1 over x ln e, but ln of e is 1. So this is 1 over x. Okay, you've got 14 things to memorize here. I'm going to talk for 1 minute more. That's it. 1 minute. Somebody start a timer. The power rule. The derivative of a constant is 0. That's easy. The derivative of x, that's 1. That's easy. These two, if you forget to memorize them, you can solve them in 30 seconds. They're not that bad. Trig. Sine makes cosine. Easy. Cosine makes sine. Easy. Except for all of the cos become negative. So cosine, negative. And cosecant, negative. And cotangent, negative. Then, here's how I do this. Out of these 4, you gotta memorize 1. If you memorize 1, you can figure out the rest of them. And here's how I think about it. I know that one of them is secant squared, and one of them is secant tangent. And I just gotta match it up, okay? Now, the way I think about it is, do I think that the derivative of secant is gonna turn into secant squared? Not really, because I think of derivatives as like degrading. So I don't really see how secant would derivative into secant. That's like an infinite money glitch kind of thing. I don't like that. So I know that that can't be true. So I know that that has to match up with regular tangent. That means I know that the other one, secant tangent, must be the derivative of secant. And then these are like the same thing. Secant, secant tangent, cosecant, cosecant, cotangent, cotangent, cosecant squared. I just think memorize 1, go for it. And then lastly, these 4 here, e to the x, ln x, 1 over x. And then these other ones, which are just a little bit uglier, you just put that little extra ln a. Okay. There's homework tonight.